Hi guys, and welcome to another of Johnny's AI Talks. Today we're going to be talking about the CBS algorithm. So CBS stands for conflict-based search. So to give you a bit of an overview of what the algorithm does, so it solves the MapF problem. So MapF stands for a multi-agent pathfinding problem. So it's a 2D map, and then it has multiple agents, and each agent has their own individual start and end point, and you have to find the route for it to get from its start to the finish point. So typically algorithms previously have used either a coupled or decoupled approach. The coupled approach is an optimal approach, and it considers all of the agents together and coming up with the best route for to get all of them from the start to end point as quick as possible. This includes algorithms like A star and ICTS algorithms. The other approach is a decoupled approach. The decoupled approach looks at each agent individually. So there's two sort of main philosophies, I guess, that you could say with the decoupled approach. One would be to look at each individual agent and find the optimal route to get it from its start to end point, regardless of what any of the other agents are doing. So think about it, if you're trying to get from Auckland down to Hamilton and you don't care about who else is going to be on the road, you just want to know what's the quickest route to get there. The other approach is that it's just a general set of rules that it gives agents, and then the agents apply these rules in going from A to B. The decoupled approach is a lot faster than the coupled approach. The main issue with the decoupled approach, though, is that it's non-optimal. So because it's not taking in all of the agents into consideration, that's not going to come up with the best solution for everyone. It's just going to look at the best solution for an individual agent, and then it might turn out that another agent's planning to be at the same place as them at the same time, and so you're going to get a collision. The other thing is that it can also not be complete. So if you take a four-way intersection, for example, and you've got cars coming from each individual direction, the decoupled approach would give a rule that says you have to give way to your right. So all of the different agents are going to wait there for the agent on their right to go, but none of the agents are going to go. So the decoupled approach can, at times, not even give a solution. So the researchers wanted to combine the optimality from the coupled approach, but also with the speed increases that we're seeing in the decoupled approach to the MapF problem. So the two-level algorithm that they developed has a high and low level. So the low level looks at each individual agent and finds the optimal route from start to finish for each agent, and then that gets combined together, all of the different paths, and the high level part of the algorithm looks at all the individual paths and makes sure that there's no conflicts. So to give you a bit of an overview of how the algorithm works, we're going to run through a quick problem. So for this problem, we've got a 4x4 grid, and we've got two agents, mouse 1 and mouse 2, and they have to get to cheese 1 and cheese 2 respectively. So first of all, to start off the algorithm, which can be seen in the bottom right hand corner, we load the problem. So we're going to load the 4x4 grid, and in this one there's no obstacles that they have to work around, so they can go to any square they want to. We're going to start off with no constraints. The solution is going to be found using the low level search to find the optimal path for each agent. That's going to be combined together and then the cost is going to be found. So there's 4 optimal routes for mouse 1, 4 optimal routes for mouse 2. All of the routes have a cost of 4. So we're going to add that up. 4 for mouse 1 plus 4 for mouse 2, going to give us a total cost of 8. So we're going to load those all into our original node. Then that's going to be passed to the high level search. The high level is going to go through each of it, starting at the initial time 2, time 3, and then at time 4 it's going to find a conflict between B3 for agent 1 and agent 2. When it finds that conflict, it's going to split up the problem into 2 child nodes. Each node is going to get a constraint that's going to avoid the issue. So the left node is going to say that mouse 1 can't be at B3 at time 4, and then the right node is going to say that mouse 2 can't be at B3 at time 4, and by splitting this up, we avoid the conflict, and then we find the optimal route without this conflict occurring. So looking at node 2, we can now go through and see if there's any conflicts, and the high level search is going to find a conflict at time period 3 where B2, there's a collision. So it's going to go through and split up that node into 2 child nodes. So for the left node, it's going to say that mouse 1 can't be at B2 at time period 3, and for the right node, it's going to say that mouse 2 can't be at B2 at time period 3. Then it's going to pass that back to the low level. When a constraint is given for the node for agent 1, it's going to find a new optimal route just for agent 1. And so that route for agent 1 is going to be updated, and then the same for the right node. It's going to do a low level search for mouse 2 with the extra constraint and find a new optimal route for that one. For the left node, you can see that the cost is now increased to 9 because it can't find an optimal route without waiting for one time period. For the right hand node, it's going to see that it's going to find a new route, and it's going to return the cost of that as 8. Alright, so the high level search is then going to look at the next lowest cost node. So there's 2 nodes that it can look at. So it can look at node 5 and it can also look at node 3 because both of them have a cost of 8. What the algorithm does though is it uses a conflict avoidance table. So what it's going to say is it's going to look at the cheapest node that's hasn't been looked at yet, but if there's 2 nodes that have the cheapest cost, it's going to have a preference for the one that has the least constraints. So that means that when it gives us back our optimal solution at the end, it's going to have as fewer constraints as possible. That means that it's going to prefer node 3, which only has 1 constraint, over node 5, which has 2 constraints. So it's going to look at that one and see that there's a conflict at C3 at time period 3, and it's going to split that one up into 2 nodes, adding a constraint for agent 1 in the left node and a constraint for agent 2 in the right hand node. Right, and now it has to decide between expanding or looking at node 5 and node 6 because they're both cost 8. It's not going to look at node 4 or 7 yet because that has the higher cost. So looking at node 5, it's going to see that there's a conflict at C2, so it's going to split that one up again, and this time it can't find any solutions without waiting for a time period, so they're both going to be 9, so it's now going to look at node 6, which still has a cost of 8. That's going to be bumped to the top of the list to be looked at. And it's going to see that that one too has a conflict at C2, so it's going to split up that one. Alright, so now we've got 6 nodes that it can look at, and it's going to look at either 4 or 7 because they only have 2 constraints compared to the bottom row, which all has 3 constraints. So it chooses node 4, and it looks through and sees that there's no conflict, so it's going to return that as the optimal solution with a total cost of 9. And then the algorithm will finish. So the researchers did a few experiments. One of the experiments was using an 8x8 grid, and it started off with 3 agents and worked its way up to 13 agents, each with their own start and finish time. That varied throughout the experiments that they did. They ran it over 100 times. There was a 5-minute time limit, so if the algorithm hadn't finished running within 5 minutes, it was noted as a failure. And 3 different algorithms were compared in the trial. So they had CBS, they had A star, and then they had an ICTS algorithm. And from the experiments on the right, you can see that CBS did the best. It outperformed the other 2, and yeah, you can see that it really started to drop off in success after it got to 11 agents. And one of the things to note is that if we look at the table down the bottom, the number of nodes that need to be expanded. So if we look at when it gets to 10 agents, it's only looking at 35,000 nodes compared to A star plus OD, which is at almost 55,000. So yeah, almost a 50% drop off in number of nodes wanted to look at. So you can see that it works quite a bit better, and especially when it gets up to the higher number of agents, the A star plus OD and the ICTS started to struggle, whereas the CBS was able to keep going for a little bit longer. Another experiment that they did looked at 3 different maps from DOA, which is a computer game. The first map in the top left that you can look at, it's a bit more open and spread out. The bottom left one is a little bit more constricted, there's a few more bottlenecks. Then the one on the top right is a lot of corridors, a lot of bottlenecks that agents can get stuck in that the solver is going to have to try and solve. So for the top left one, the ICTS did a lot better than the others. CBS did the worst. And the bottom left one, CBS was about average, a little bit worse than the ICTS, but still better than the A star. And then in the top right one, the CBS did the best. So from this, the researchers were able to say that in general, the CBS is going to do better when the map is more characterized by bottlenecks and corridors. At the moment, there's still not a really good way of characterizing maps and breaking them down to say before any algorithms are even run which one's going to do best. But from this, it can be seen that CBS typically, if you're going to have a lot of corridors or bottlenecks, could be a really good one to try. If it's a lot of open spaces, then CBS might not be the best algorithm to use. So, impact on applications. It was found from the experiments and from the research that's been conducted so far that we still don't have an optimal algorithm for all maps. It really depends on the map itself as to which algorithm is going to be best. The CBS algorithm was found to do better than the other algorithms tested for congested maps where there's a lot of corridors, a lot of bottlenecks. But as of yet, yeah, we don't have an optimal one, so it really depends, and trial and error is needed to find which one's going to be best for your map. The CBS algorithm is a big step forward in breaking down that continuum of either being a coupled approach or a decoupled approach, and it can be used in applications such as video games where you've got maps and you have to try and get from A to B as quick as possible, robotics, and also vehicle routing and planning your route. Yeah, so that's us. If you like the video, definitely check out the link below. The researchers have done one step better. So the research article that we were looking at was from 2012. They've come up with a new one, which is an improved CBS algorithm, which looks at including meta agents. So if two of the agents are colliding too often, then it restarts the problem and actually combines those 2 agents into what's known as a meta agent, and then they've got some other really cool improvements in there. So yeah, a link in the description below. Definitely go check it out. If you like the video, subscribe, hit us up with a like, and thanks for watching.